Hello, everybody. For those who don't know me, my name is Danny Sierra. I'm a professor at University of Illinois, Chicago. And it is my great pleasure to introduce Professor Derek Frydel, who's coming to us all the way from Chile. He's a professor in the Department of Chemistry at the Federico Santa Maria Technical University. He did his Ph.D. in theoretical chemistry here in Chicago at the University of Chicago, after which he did a worldwide tour of postdocs from Max Planck Institute, Tel Aviv University, to the ESPCI in Paris, and down in Brazil. After which he got a position in China, and now he's in Chile. Professor Frydel's work focuses on statistical mechanics and how that ties in with chemistry, colloidal physics, electrostatics, and more recently, non-equilibrium and active matter physics. And something that really strikes me by a lot of Derek's work is that he really focuses on getting a lot of mathematically tractable analytical results in regimes that people typically might not be able to find them. And so I think he fits right in here at NITMB. And so please join me in welcoming Derek, and excited to hear what he has to say.
So thank you, Danny, for this introduction, for inviting me for giving this talk. The description of my recent work was very good. I mean, I focus on these analytically tractable models that no one tries to look at. So a little bit of the background. So for my PhD in Chicago, did a lot of simulations on colloid particles. Then for my postdoc, I switched to electrostatics, and I worked for many years. And I switched again to non-equilibrium statistical mechanics during COVID era. It was a good moment, I think, to start something new. So let me give you okay. So the talk will be divided mainly in two parts. So the first part, I will talk about the splitting, the relation of the splitting probabilities. I will explain soon what's the splitting probabilities, and the stationary distributions, okay? Then the second part, which is more recent, I'm still working on it, so I don't know how much time we'll get to discuss the second part, is on this Brownian particles or active particles and periodic force fields, okay? And in these systems, we have the emergence of the effective diffusion constant at long times. So I will again discuss it. Okay, and the relations that I discovered in my work turned out to be discovered previously 50 years ago, 1976, by Zygmunt. Okay, so I will briefly, So originally, when I worked this, I thought I was the first one to find these relations between stationary distributions and first passage quantities. Okay, again, I will discuss first passage quantities soon. The idea is that the first passage quantities are generally formulated. So within the backward Kolmogorov equation, stationary distribution are formulated within forward equation. So the forward equation is what we usually refer to as Fokker-Planck equation. So I don't know how familiar are you with the statistical mechanics. So basically the idea is you look at your formulation of the, for example, splitting probability within this backward differential equations, you compare to some stationary distribution, okay, and you try to make them similar, and then you arrive at these relations, at these identities. So that's the idea, okay. And basically last month I discovered that these relations were studied in 1976, and also the application of the relation was also published in 2024 recently, okay, in active matter. Yeah. So a manifestation of duality on the Ran and Tambo particles. So I start with I think this is like the ideal guess of the active particles. This is as simple as it gets, okay? So people started mathematically study the system when the microscopes became very powerful and they were able to follow the motion of the bacteria. And these biologists determined that this bacteria's motion has two stages. The first stage is deterministic, so the particle or the bacteria moves in straight lines with constant velocity for a certain amount of time. the experimental results were sufficiently accurate. So these people were able to determine that the duration of each run stage obeys the exponential distribution. This is very important because exponential distribution is considered to be memoryless. Okay, and then there is instantaneous. At the end of the run stage, particle tumbles, so it changes its orientation and it chooses any orientation. So there's no preference for the orientation. Okay, so there's a tumble stage, and the tumble stage occurs instantaneously in my model. So that's the model. Okay, so now let's imagine, so there is no diffusion, there's no thermal fluctuation. So these particles, we can ignore the fluid, okay? And there's only this bacteria motion, particle moving between two hard walls. Okay, so what happens is these bacteria in the space between the walls, they move freely, they change their orientation, but once they hit the wall, okay, so because this over damped limit, particle does not bounce back, but it continues pushing. Okay, so because it continues pushing, it creates a kind of adsorption. So I call it dynamic adsorption. It's not the adsorption as a result of the interactions between particle and the wall. This is dynamic. The adsorption has a dynamic origin. Okay, so these particles stay adsorbed for some time until they change their orientation and then go back. So if you think about stationary distribution, the stationary distribution will have two types of particles that are adsorbed, and you can represent these particles with a delta function, and particles that are moving freely. Okay, and I will try to relate this to another problem. So now I introduce the concept of splitting probability of the same particle. So let's say that our bacteria starts at this wall, okay? Then it moves in straight line for some time at constant velocity, but the length of each jump, as you see it, depends on the time, okay? And the time, again, I remind you, is drawn from the exponential distribution. So this particular trajectory is successful trajectory. So the successful is that it reaches the other wall without ever crossing the first wall, okay? So if you want to calculate splitting probability for the particle starting at the wall, okay, then you run simulations, you generate a lot of trajectories, then you count all the trajectories, and then you count the trajectories which are successful, and you divide the number of successful trajectories by all the trajectories, and you get splitting probability. Okay, so that's the idea of the splitting probability. So what I will try to find the relation between the two. Okay. Okay, so this is so to do it, okay, initially how I did it, okay, for the run and tumble particle, I said something like this, that okay, maybe we could simply map our run and tumble motion into this jumping particle. So let's say, in other words, let's ignore the positions of the particles within the run stage, and we only record the positions at the tumble stage. Okay, so at the end, if you do it, if you do it, you don't actually calculate stationary distribution, but you calculate stationary distribution of the tumbling events. Okay, so normally they're not the same, but because the time duration is drawn from the exponential distribution, which is memoryless, it gives you the same distribution as stationary distribution. Okay, so this exponential distribution of waiting times is very special. Okay? So that's what I'm going to do. So first, this is the observation. I make the observation that we don't need to sample particle position at each moment, but we can sample it only at the end of the run stage. And based on this observation, I'm going to build a framework. Okay. So first, I need the distribution of jumps. So let's say particle is initially in a run stage, which is deterministic. Let's say particle is initially at x equals 0. So the question is, what is the position of particle in time t? Okay. So this is deterministic. So velocity. Okay. We have certain velocity. We have certain time. Okay. So this in itself is deterministic, and this deterministic distribution is defined by this delta function, which is like propagating delta function, okay? But now there are different times, okay? There are different times, the different durations of this process, okay? So we have certain distribution of the durations, okay? So we integrate by this. Then there's also different distribution of velocities, okay? So now, and then, so that's how we calculate your distribution of jumps, okay? So just to remind you, okay, because I introduced this distribution of waiting times, which is exponential, so I'm repeating this. But the distribution of velocity, remember, is actually the projected velocity. So if the particle moves not directly perpendicular to the wall, it will have velocity v0. Okay, but when I move now to the wall with this orientation, I will approach the wall much slower. Okay, so this v actually represents the projection of the velocity, swimming velocity. So for this reason, okay, we have different distribution for different dimension. Okay, so dimensionality of the system enters through this distribution of velocities. Okay, so now this is the integral equation for calculating stationary distribution. Okay, so I'm calculating stationary distribution. Here I have to emphasize that this stationary distribution is not normalized to 1 because the stationary distribution does not include these particles which are dynamically adsorbed at the walls. So these are represented by some delta function. Okay. So when we start at some position x prime, then this particle jumps to a new position. Okay, and we also have certain distribution of these particles. Okay, so at each x prime there's certain distribution, and if the system is stationary, it should not change the distribution. So they should be the same. Okay, here we have contribution of the delta functions which are at the walls. So Fw represents here fraction of adsorbed particles at a single wall. Okay, for this reason, this entire distribution does not integrate to 1, but yeah. Something like that. So these are the contributions at the wall. Okay. Now let's go back to the splitting probability. How to calculate, how to arrive of the integral equation for the splitting probability. And so the idea is that we can consider, we can split the formula for the splitting probability for the probability for the particle to reach the other wall at a single jump. Well, it's possible, okay? Maybe if the walls are separated, maybe it's almost 0. But there's a probability to reach the other wall at 2 jumps, okay? So we represent this entire, I'm sorry, I need water. Okay. Okay, so the splitting probability basically the sum of all these probabilities, okay, to reach the wall in a single, 2, 3, 4, etc., jumps. Okay, so the distribution, so the probability to reach the wall, okay, from any point x within this integral is this integral. So let's see if it makes sense. So we calculate. So this g function, it is normalized, so it integrates to 1. So all the jumps that go beyond L, okay, we integrate it and it represents the probability to go to cross the wall. Then there's also this iterative equation. So basically, which I will not spend too much time, but if you put these 3 equations together, you end up in this renewal equation. So I call it backward renewal equation, okay? So now I have derived these 2 equations for the stationary distribution, the other, I call it forward problem, okay? And then for the splitting probability, something that looks very similar, but it's not exactly the same. So when I work on this paper, I was only interested in this formula, and I started searching on Google of some other problems involving maybe active matter that also involved some kind of integral equation, and I stumbled on it. So I stumbled on it by accident, and I just wanted to compare it. And initially, I did not see a similarity, but then if you integrate the splitting probability equation, you end up in something that looks like my stationary equation. So based on this, I said, okay, I found this relation that the derivative of the splitting probability is actually the same as the stationary distribution. But for me, most important was this observation that the fraction of adsorbed particles, So let's say you have a stationary system. So the fraction of the adsorbed particles is somehow the same as the splitting probability or the probability to reach the other wall. So this is something, on the one hand, it's very, should be intuitive, so some connection, but I don't think I would be able to put this relation just based on some physical intuition. So I think all these machinery was kind of necessary to arrive at this very simple relation. Okay. To this day, I'm not sure if I can explain it intuitively. This why fraction of the adsorbed particles in a stationary system should be the same as the splitting probability or the probability to reach the other wall. Okay, it kind of makes sense, but maybe there should be constant, yeah, something like that. But this is the exact relation. Okay, so those are the results. This is the paper that where I found the splitting probability equation, and what they said in this paper so they studied jumping particles. Okay, our round and tumble particles is not a jumping particle model, but I can map it. I can treat it as a jumping particles, and they said this particular discrete jumping process generates something that is that gives splitting probability that is not zero. Okay, so okay, I have to okay. So the main point, so when the jumping particle starts at this wall, okay, there's a finite probability to reach the other wall. But if I'm a Brownian particle, okay, so I will never reach the other wall if I start from this wall, because there's always, because Brownian particle is actually fractal, so there's always a path that will cross back to this wall, okay? So basically what the authors say that, that this jumping process gives something that Brownian particle does not give, okay? And so I was wondering I found that this condition, okay, the splitting probability at 0 is greater than 0, is not restricted to jump process, okay? Because round and tumble particle is an active particle. So maybe this is something general for any active particle. And yeah. Okay, so here I explain what. Okay, so this is exact formula for the splitting probability of the Brownian particle with the drift. So even if the Brownian particle is at this wall and it has a drift toward this wall, it will never reach the other wall. Okay, so the probability is 0. Okay, and it has to do with the fact. So if you look at the microscopic description of the motion, so here's the drift away from the wall. And here's the Brownian motion, okay? But we know that this Brownian process is proportional to this root square of time. So this at the small time, this process is dominated by the Brownian motion. So this drift does not change this, okay? So even if the Brownian particle has a drift toward the wall, it will never reach the other wall, okay? So if you, okay, so I skipped this. This is another way of explanation. Here is another model of active particle. This active particle model is called Ornstein-Uhlenbeck particle. So let's see how it works. So basically, the change of position is proportional to velocity, some velocity. Okay, and there is no Brownian part in this formula, like unlike in the Brownian motion. So the Brownian motion only enters and governs the evolution of velocity, okay? And because of that, because it's not directly here, okay, the Brownian motion is in velocity, so when you try to integrate it over some time, and then you see that at the small time, the change of x is dominated by this drift term. And the Brownian motion only enters in the higher order terms. Okay, so at the small time there's enough. So even if the active particle motion is continuous, there is enough time. There's enough possibility to move away from the wall. And once the particle moves away from the wall, it can reach the other wall. So that was the microscopic view of this. Okay, but now I needed to prove it. Okay, and so how to prove it? So for the round and tumble, okay.
Want to ask you about time and length scales. So if I understood correctly, the two walls are perfectly absorbing, right? So once a particle hits one of the walls, it cannot detach. Correct?
For the boundary condition, yeah. So for the stationary position, no, there is no absorbing particle. So the walls only don't allow particle to move from. So there's no absorption involved. So it's purely dynamic absorption. So yes.
So I was wondering, like, whether the system size matters. So if you have, I don't know, a distance of L, what is the upper time that a particle that starts at the middle, let's say, can hit one of the boundaries? That's one question, and that is related to this here because the run-tunnel motion on short and time and length scales looks a bit different, right? It has these continuous jumps on the path, and the Ornstein-Uhlenbeck process leads to a continuous path.
It's a continuous, right?
So I was wondering whether that plays a role, like if you have a transition, if you change the length.
So there's no transition. I did not find the transition, so I move a little bit ahead. Okay, so.
In other words, does it matter that the path is continuous or not? Is that relevant? Or because the ensemble trajectory is not continuous, right? On short length and time scales.
So okay, so in this, so what I show is the fraction of adsorbed particles. Okay, fraction as a function of length of the plates, but the length of the plates is divided by the persistence length. Okay, so the persistence length is velocity zero of the Bergman particle times the tau, and tau represents the medium waiting times in a specific direction. Okay, so so for all these models, far away from the when the distance is large, this behaves as 1 over lambda.
Right.
Okay. Yeah. So that's something. Only when the okay, but so
thank you.
Yeah. Okay, so we are here. Okay, so the next goal. Okay, so the next goal was to find a framework which where I could show that this fraction, the finite fraction of adsorbed particles, is somehow related to this finite splitting probability. Okay, but for the RTP particles, I was able to use this integral equation, this renewal. For other particles, I cannot do it. Okay, but what I could borrow from the previous method, that I could also do something similar. I could define forward equation and the backward equation. Forward equation for the stationary density. Note that this density now is stationary, and so the phase space now depends on the position x, but it also depends on the velocity. Okay, so we expanded this the phase space. Okay, the same with the splitting probability, because for these models, in order for the process to be Markovian, we need to expand the states phase space to x and v. Okay, so we will work in this space. Okay, so I will try to borrow from what I will not borrow is the exact framework, but what I will borrow is to play around with the forward and backward equations. Okay. So here to make I want to work with the 3 different active particle models, and to do it in a single framework, it took me some time, but okay, so it helps to renormalize the distance x by the persistence length, okay, by some characteristic assuming velocity. So for Rahn and Tambo particle, for the active particle model, this velocity is constant. For Ornstein Uhlenbeck process, this is it has another formula, but anyway, we can define it. So now length I divide by this persistence length. Okay, so the separation between the 2 plates. The velocity I divide by this velocity characteristic velocity. Another thing that was essential for me to simplify my equations was to represent this dense stationary distribution, which is in z, okay, in the position and in velocity, in this form, and so basically, I take and I multiply. Okay, so I separate the distribution and the velocity with this velocity, and then the framework simplifies. Here's also definitions. So we have to remember that this quantity is not normalized to 1 because there's a fraction of adsorbed particles again. What else should I say? Okay, so now also the particles which are adsorbed, we just don't say that they are adsorbed. We also we need to we have certain distributions. So the particles are adsorbed in a certain orientation toward the wall. So there are some particles who are pushing directly at the wall. There are some particles that move in this direction. So it's a certain distribution of velocities. Okay. And so this is the forward equation for all these active particle models. This is the forward equation. So the stationary state, this part is 0. This is diffusion, not diffusion. This is drift. Okay, V. And this part controls the evolution of the velocities. Okay, and for the 3 models, we have 3 different. This operator is very different. So for the active Ornstein-Uhlenbeck model, this is governed by the diffusion. Okay, so this velocity is diffusing, but this velocity is diffusing like in a harmonic potential. So it never goes to very infinite values. Okay, so basically this velocity. The mean is 0, and it fluctuates under this value. For the Rahn and Tambo particles, what we have is there's a rate that the particles in a specific velocity vanish at certain rate, but then the particles from other velocities change their orientation to the other orientation. So we have this integral form. Okay, and this distribution of velocities depends on the system dimension. Okay, and for our active Brownian particle, I get something like this, which looks a bit like this part, so like a drift, a bit like a harmonic potential with this kind of like velocity dependent diffusion. Okay, so anyway, so I will now play the same game. I now have a forward equation and I have a backward equation. So the difference between forward equation and backward equation is very simple. Here we just have plus sign and this is minus sign. Okay, so the difference between splitting probability and the stationary distribution is just the boundary condition and the sign. Okay, so now I will try to make these 2 equations look similar. So that's all. So now I'm playing with the mathematical structure. I forget about physical intuition. So I'm going to try to make these 2 look the same. So the first thing that I do is I change the sign. And then when I change the sign, so I no longer have a physical distribution, but I have another distribution. So I call it this dual distribution. Okay, so it's a weird system. It means that the velocity is this in this direction, and the particle moves in this direction. Okay, so imagine that we write some kind of simulation that says, okay, if the velocity is positive, instead of moving in the positive direction, I'll move in the negative. Okay, but we can clearly conceive of such a system. So the relation between physical distribution and this dual distribution is just this symmetry relation. Okay, so that's all. So it's no problem. So this dual distribution is pretty much related to this distribution. So okay, so now we have the same differential equation. What is still different is the boundary condition. I will not spend too much time on this boundary condition, but they are different. Okay, so we will try to make them the same. So to make them the same, I now start to play around or change the backward equation. So I take the derivative with respect to z. Okay, so I introduce this new quantity, which is just the derivative with respect to z. And it still obeys the same differential equations. Okay, but now the boundary condition change. Okay, I can get the boundary condition, and they look very similar. Okay. So now I introduce this dual distribution. Now I also introduce this something that is related to the splitting probability. But because of the boundary condition, I cannot say, so I can only, at this point, I can only say that this quantity is proportional to this dual distribution. I cannot yet say that C is 1. Okay, for Rahn and Tambo particle, I will go quickly. I can show that the C is 1. Okay, it's pretty straightforward. Okay, for the other models, I can also show it, but it requires more mathematics. But we end up in this relation. Okay, so this is by playing around with the backward equation and the forward equation, I find this identity, this relation between dual distribution, stationary distribution, and this quantity. Okay, so now I have this distribution. I go back to the original definitions. So we define this as this. Then I remember the dual distribution is related to the physical distribution with the symmetry relation. Also, we introduce the separation of the stationary distribution. And when we do it, we this relation changes to this one. And when we do this, compare the same thing for the boundary condition, we have this relation. Now I integrate it over all the velocities, and I end up with this relation. So this relation, remember, I found it for Rahn and Tambo particle using the renewal framework, okay? And so now I see that this relation works for all the active particle models. So it wasn't just special for Rahn and Tambo, okay? This relation I also established for Rahn and Tambo particles within this renewal framework. Now I use this other framework and I end up in the same relation. So the previous relation, which was derived for Rahn and Tambo particles, seems to be uniform for these active particles, okay? Okay, and so the final step was to use the simulations, okay, to compare. So these are for the 3 different Rahn and active particle models in 3 dimensions. So the particles are between 2 walls, and I calculate stationary distribution. I let particles move around, and okay, they stick to the wall. And collecting data, and enough data, I can calculate the fraction of adsorbed particles. Okay, that's pretty simple. And then I compare it with the splitting probability. That is the probability. I start with the particle at the one wall, and I calculate trajectories to reach the other wall, and then I calculate the number of the successful. So what's the advantage of this relation? Okay, so well, it's a nice identity. Okay, is it useful? Doing the numerics, I discovered that it's much easier to calculate fraction of adsorbed particles than the splitting probability, much faster. Okay, so that's why I have less points for the splitting probability, because the simulation then, when the system becomes larger, like 5 here, this lambda, and again, lambda represents length between the 2 plates divided by the persistence length, okay, then it becomes much more difficult. So the simulation, even for such a simple system, take a long time. On the other hand, when I do the stationary distribution simulations, they are very fast. Okay, I will skip that. Okay, this is the second part. Okay, I'm changing the direction of the subject matter a little bit. So I will continue with the duality relation, but I will apply it to a different system. Okay, so when in 2022, so in Chile, we had COVID, quarantine was very strict for 2 years. So first year, I thought it was pretty interesting experiment, pretty fun. But the second year, I said, I need to, I don't know, change the research topic or something to get myself occupied. Yeah. And so I decided to study. At that point, I decided to study in non-equilibrium statistical mechanics. Also, my international collaborations, the communication was not very continuous. People had their problems, etc., etc. So I started working on this on my own. And so I basically printed several fundamental papers that I could find on non-equilibrium statistical mechanics. And this was one of them. And I said, okay, so I need to understand these papers in order to enter the field. And so the idea is that these systems are periodic. So here we talk about there is no active particle. It's just a Brownian particle. So the Brownian particle, it moves in this periodic potential. For simplicity, I put it as a sinus potential, cosine potential. The system is also, the particle is also driven, okay? Can be driven, doesn't have to be driven, okay, in this direction. And the system repeats itself, okay? So you can kind of coarse grain it into cells. Okay, so this is another view. Okay, so what happens is at the long times, what emerges is an effective diffusion. So the effective diffusion is not the same as the thermal diffusion, it's something else, okay? And when there is no driving force, this effective diffusion is less than the thermal diffusion, which kind of makes sense because now a particle needs to climb this hill, then go down, so it slows down. So this periodic fluctuation modulation kind of creates effective friction, okay? But what happens is when there's a driving force, the effective diffusion can be enhanced. Not only so, but what emerges is what people call is giant diffusion, okay? So I wanted to understand it. So in this paper for 2001, they came up with the different formulation. This formulation of the effective diffusion is based on the first passage time. Okay, it's based on the first passage time. So it looks very similar. Here we have a mean square displacement. Here we have the second moment of the first passage time. Here I need to specify that this first passage time is, let's say, from this position to x plus L. It's never to the other cell backward. So when the particle for some reason goes back, we don't consider it to switch its cell. So it only counts the jumps to the cell in the direction of the driven force. Okay, so the authors in this work derived it, and at that time I knew nothing about first passage time. Okay, so I did this physical chemist thing. I took their formula, the final formula. I'm not going to provide the formula for this E terms, but they're very complicated, and I try to put it into a different form that maybe to me it would make more sense. Since I didn't know much about first passage time, stationary distribution made sense to me more, and I came up with this formula. So I'm basically doing back engineering, doing nothing else. So I came up with this formula, and I thought, okay, so I come up with this stationary distribution, but which is the force is in a different direction. So I thought, okay, so it's very intuitive because all the quantities are the stationary distributions, but I could not explain it. I tried to share this idea with some colleagues, but they look at me strangely. So I thought maybe I should keep some thoughts private, so I didn't share it. Okay, so but anyway, so this dual distribution is for the same system, but we change the force. Okay, but now after having done this previous work which I presented, I decided to revisit this problem. So I said, okay. So I said, well, since this formulation is in first passage times, and in my previous work, I was able to come up with the identities, these relations between first passage time and the stationary distribution. Maybe now I have tools to derive this equation, not just convert this equation into this, but derive it. So provide the rigorous explanation. Okay. So basically, this is the dual system. So look, the physical system is this one. So here is the valley, and the valley here in the dual system corresponds to the hill. Again, hill here corresponds to the valley, and we also change the driving direction. Okay. So what's the interest? So for some reasons, you can form the formula for the effective diffusion based on these two systems. Okay. So now I will try to derive it. Okay, and I think I have time. This is actually something that I'm working on, and I usually enjoy talking about problems that I have not yet solved. I'm working on. I'm much more enthusiastic. So to do it, I had to be very persistent and very stubborn. For some time, I could not find anything. Okay, so I stumbled on something called homogenization. I don't know how many people know of homogenization. I discovered it basically a couple months ago. And I discovered it in a mathematics journal. Okay, so if I look in the history, it was developed in the 50s, 70s for the transport in heterogeneous media. For example, it's applied. I understand it's applied in the porous media. So porous material has a lot of macroscopic details. So people try to eliminate these details and come up maybe with some effective diffusion or whatever. Okay. Then, and it seems that in this year, 78 or 87, it was the formulation that I think I'm using now will be from these years. Okay. So what's the idea? Okay. So the idea is our microscopic Brownian particle moves in this periodic force, which can also include the driving force, and there's a Brownian motion. Okay. So this force field is periodic. Okay. So now, I'm just following a little bit since I did not derive the homogeneous, I did not participate in the formulating the homogeneous. I follow the formulation. So they introduce this alternative process. They take the original physical process and they remove everything which is systematic. So we have some systematic velocities. Since if the system is driven, the particle will not be moving will be moving in a constant force. This force will not be the same as the driving force because we have our hills and valleys, maybe a little bit slow, but the entire system moves in one direction. Okay, so first thing we eliminate this deterministic systematic motion in one direction. The second thing is anything else, anything because our system is periodic. So there should be some contribution, some systematic deterministic contributions from this periodicity. So people in this homogenization field call it a corrector function. And they put it plus because I think they were thinking like mathematicians. So let's add something which corrects our process. So we don't know yet what this corrector is, but we want it to be such a function that it eliminates everything deterministic. Okay? Okay, so now I take the derivative of this process. Okay, I get this. To get formula for this, I had to teach myself Ito calculus for the first time. Okay, so I get this. Okay, so now I get this formula for this process, and I don't know what this form of this corrector is, but I want it to be 0. Okay, because I want all the systematic motion to vanish. I only want to capture fluctuations. Okay, so whatever this corrector is, it should satisfy this equation. Okay, so basically now I get the differential equation for the corrector, which I postulated. I didn't know exactly what it obeys, but based on this, I get this differential equation. It turns out that this part corresponds to the backward differential equation. So once I get this backward, except it's not 0. Remember, for the splitting probability, we had the same equation, but here was 0. Here, this equation is like the Poisson equation, okay? But once I got backward equation, I already know the game, how to play around, how to modify it into forward equation, okay? So that was the essential step, okay? So now I will play this game, rearrange the backward equation, like the Poisson equation, in this form. Okay, so I carry this force to this side. I also introduce it here, which is the one I introduced here doesn't matter. So I only left with this constant. Then I differentiate it, and I also divide it by L length because I wanted to have some units of length, okay? Or 1 over length, okay? Because I want it to be distribution. So I'm forcing it. I'm forcing it to be distribution. So I do it, and then I define that this quantity, since it is periodic, since this quantity can be shown to be normalized to 1, okay, and since this quantity has a correct 1 over length scale, it must be distribution. And so when I compare this equation for this dual distribution with my original equation, I get f to minus f. Okay, so I get this view. So this is so I stumbled on this dual system which goes in the other direction. Okay, so what I previously discovered by doing this back engineering relation, now I discovered that this dual distribution actually has the physical significance. Okay, anyway, so this is 0, so we can eliminate this, and we are left with only with this part. So whether not correctly, I identify this term as the local diffusion. So mathematicians don't do it. Probably mathematicians would not be very happy for me to do it, but I call it like a local diffusion. So if I eliminate from my process all the systematic processes, I only have these fluctuations, and this fluctuation depends where particle is in a cell. Okay, and then this local diffusion corresponds to this function in terms of corrector function, but then I identify this corrector function with this dual distribution. So now I can identify this dual distribution, square dual distribution with these local fluctuations, okay? But I still don't have effective diffusion. So I need to, effective diffusion is a long time. This is diffusion and local diffusion within a cell. So to do this, so I integrate this process. I square it, then take the average, then I use this, and so I end up in this formula, and then using ergodicity, that it's sufficiently. So I am basically saying that at a very large time, sufficiently large time, particles end up in a different cells, but their distribution within these different cells is the same as the stationary distribution. So I do this ergodicity trick. Okay. Yes.
The boundary conditions.
Okay, periodic boundary conditions. Thank you. So thank you. So it's a particle. So I only treat a single cell. So the stationary distribution is here because when the particle enters here, it's still it's a repetition. So the moment it leaves, it enters here. So it's periodic boundary condition. Yeah, thank you. For this reason, this is not an equilibrium system. Okay. Okay. Yeah. Okay. So now this is the definition. Okay. So now the effective diffusion. Yeah. So the effective diffusion can I define it this time. It is local diffusion. And since I defined it before this local diffusion, I end up in this equation. So what I kind of postulated, not understanding this formula, now I can prove it. Okay, using this duality relations. But in this case, first passage time was not very useful. I had to find this homogenization framework. Okay, so. Another thing, this symmetry relation. So the effective diffusion doesn't matter if the system goes in this direction or this direction. The effective diffusion is the same. So you can actually define it as like this, or you can define it like this. Okay. So the effective diffusion will be the same. Okay, regardless of the direction. Okay. Yeah, and I don't know if I should because this section. Maybe I say, okay, so what's, well, maybe this is not a big deal, but you can expand this this framework. So I will go quickly now. You can expand it to the system where the force fluctuates. So before our force, periodic force was fixed. Okay, but now let's say our force fluctuates, the periodic force. So maybe it disappears and then appears, disappears, appears. Okay, some kind of fluctuations. So this is actually more important. So I assume that. The only assumptions I make is that the waiting time or the time that the system stays in a particular state is drawn from this exponential distribution because I don't want to introduce any memory effects. I want to make my life as simple as possible. Okay, so if I do it, then I introduce additional parameter, the position of the particle and the sigma. So the force now depends on the sigma, but the sigma fluctuates. Okay, so I skip all these things and then yeah. And I get some for this system I get some a different expression. Okay, so this expression looks similar to what we have seen when the force does not switch. So this term is similar, but we have this additional term which depends on tau, and tau is the average or mean time of the waiting time that the system stays in a given state. And here, so I introduce the dual flux. So it's the same as the physical flux, but the flux is in the other direction. Okay, so this formula is pretty new. Like this formula, I could say that you can obtain it from the previous work, but this is totally new. So I am able to define the effective diffusion totally, completely in this dual system. Okay, and I will wrap up. So this is something, okay, so I decided to test my formula. Okay, I decided to work on the two-state model. So the system fluctuates between this force and this negative force. Why I chose this system? Because this negative force is dual force. Okay, so it's self-dual. Okay, and I get this expression. I can simplify it. Okay, I'll go and I try to consider some simple analytical case, some triangular system, and I get this expression. So I get I get this expression. Okay, now bad news. The expression that I got does not agree with what is previously reported in literature in 2006. They get something different. So I thought, okay, so my framework is wrong. I tried to rederive everything from the beginning. I did not find an error. Well, but and then I decided to do simulations to compare my result from the reported in the literature. So my effective diffusion is, I will explain what it means, is this value. Okay, the report is in this value. So maybe the difference is not huge, but there is difference. Okay, so I have to explain a little bit how this reported case was derived. So basically, this case assumed that each cell is independent. Okay, so they use this formula. This is basically the mean time to leave the cell. in any direction, to the right or to the left. This is the mean time when the particles in a positive state, because there are two states. The system fluctuates between two forces, and this is the mean first passage time when the particle starts in the negative state. Okay, so I will not go deeply into this formula, but it makes this formula is correct if the periodic force does not fluctuate. So I don't know what the reasons. So there was assumed that it should also work when the force fluctuates. Okay, but now if this is correct, then it doesn't matter if the cell has this size or this size. So if the cell has one periodic length, 2, 3, 4, 5. Okay, so that's what I do. So they based their formulas on assuming that each cell is independent. So they get this. But now let's say you assume that your cell has this 2 periodic lengths. Then suddenly they're using the same formula, goes down toward my value. Then 3 cells, 4, 5. So if you go to infinity, it converges to my value. So and the idea is that my framework, the framework that I derived apparently is correct. Okay, so it's not wrong. So I have proof. Okay, so I will complete my talk here. I will only say that this fluctuate. Okay, the only thing I will say is that this fluctuating periodic force can lead to the enhancement of the effective diffusion. Okay, so if I increase my this is the function Peclet number. Peclet number basically depends on the tau. Remember, the tau is the waiting times. Okay, so there's this. So with the periodic potential fluctuates at certain frequency, then there's this peak. There's this maximum. Okay, so anyway, here I don't need driving force. Here I don't need a driving force. I only need that this periodic potential fluctuates. So here I have no periodic force. It only fluctuates, and it's enough to produce this giant effective diffusion. Okay, and I will complete this. Thank you for your attention. And I have to give credit to the Fondesit for the research grant. So thank you very much for attention. Thank you very much for inviting me, and I hope you gain something from this talk. Okay.
Any questions for here?
We can also talk afterwards. Okay. Yeah.
I want to ask, like, if you only have a Brownian particle in a fluctuating periodic environment, then you can, by having the right on-off switch, produce what people call Brownian ratchets. And I was wondering, like, this enhancement of the effective diffusion coefficient that I guess you see in the environment where you switch on off, right? Is that related to this kind of effect, or what's the mechanism that leads to enhancement?
Yes. So normally, like if you have no fluctuations, you need a driving force. So for me, this was new. So here for me, I discovered it that you don't need a driving force and you have fluctuations. But I think maybe what you referred to is people mostly study these periodic potential which are not symmetric. And so when the fluctuations happens, the particle is not only diffusing, but it's moving in a certain direction. So I think this is of the bigger interest than this system. And I haven't yet tested my formula on that.
If you have asymmetric potentials, would you then I guess it's not true that you have the symmetry, right?
No, the symmetry will break. Yes. But I haven't examined it myself. But for reading the literature, yes, that's what I get. Yes.
I also have a question.
Okay.
Yeah, so for the first part, you have this dynamical absorption,
yes,
right, into a wall. This is also the mechanism by which active Brownian particles, for example, will have motility-induced phase separation. So you have particles that will meet a big blob of particles and then just stick there. Have you thought at all about using this as a sort of different the duality that you have as a different lens to understand this phenomenon?
It did cross my mind, but at the moment I don't have. I would have probably started to work on these many particle systems, active systems, to have understanding. So I don't have at the moment. I don't have a theoretical understanding, but this would be very, very good direction to try. Yeah, eventually, but it will be difficult. I think. But we can talk later at
Yeah,
the
well,
lab.
yeah,
So-
Derek is around today. Thank you all for coming on a Friday in the middle of the summer. And yeah, let's thank him again.